I would have wanted you to use what we've been talking about in class, but there's more than one way to solve this question. I would wanted you to think about the work-energy theorem, which states that work is a method by which you change something's energy. There's a single force acting on the car here. Well, single force that's doing work on the car. This is the car, and it's got a velocity in this direction. Then friction is acting to stop that car. Of course, there are other forces acting on the car. Neither of those can do work on the car because they are perpendicular to the displacement. So the work being done on the car is being done by friction. How much work? Well, force times displacement times the cosine of the angle. The force is the frictional force. The displacement, 40 meters. The angle, 180 degrees. Any question where I got any of that from? Now look, the force isn't a surprise. The frictional force is something we know. We know that friction is equal to mu times the normal force, and in this case, that's mg. I'm not going to wait around for you guys to do this stuff anymore. You guys can do this. We've done this enough times. It's level ground. Normal is mg. Friction is mu times normal. Meaning this becomes mu mg times 40 times -1. That's how much work is being done. And I don't have an answer there because I don't know what m is. I do know, however, that this is going to cause a change in the kinetic energy. Change means final minus initial. Look, the car is brought to rest. Its final kinetic energy is 0. So this will equal -1/2 mv initial squared. I don't need the mass of the car. You have everything else. You can figure out v. I'm not interested in your algebra. I wanted to see you start here. I wanted you to think about this. I don't want you to see if you could work the pieces out. I'm confident at this point you could tell me what v equals, but I'm not really that interested in that number. Do we understand what I'm trying to get at? Tomorrow we're going to try one, for real. And I'm giving you about this amount of time. Everybody understand? Any questions? Look, I am just picking one of your homework questions. I'm going to ask it nearly verbatim tomorrow. If you've done your homework, you're going to be able to do it, no trouble. I'll even let you have your homework out. Or I'll pick one next to one of your homework questions. You know, the odd number or the even number. I don't know. This is where the notes really begin. We're looking at the topic of conservation of mechanical energy, which is where I left off at the very end of class yesterday. Conservation of mechanical energy. This topic is, energy is always conserved. I want you to go into this idea first, that energy is always conserved. Any force that acts on an object is simply transferring the energy from one form to another. The problem is that some forms of energy are more useful than others, meaning that some forms of energy, you can get the energy back into mechanical energy, specifically kinetic energy. Remember, the idea of energy, the most basic form, is movement. So any form of energy that allows you to get back movement is considered a mechanical form of energy. Unfortunately, there are lots of forms of energy that aren't mechanical. Friction. Friction is a force. It creates heat. Thermal energy is a form of energy. But you can't make the heat that is taken away by friction make an object go faster. It just doesn't work that way. However, all forms of energy are conserved. I mean, you can always account for all the energy. But for problem solving, sometimes we look at making an estimate. We look at a system where there doesn't seem to be any external forces acting on our system. We say that mechanical energy is conserved if there's no external non-conservative forces acting on the system. Conserved. Again, we say that mechanical energy is conserved if there's no external non-conservative forces acting on the system. So if there's no friction or air resistance or all the things that we know really exist, then the mechanical forms of energy are conserved. Now, just so you guys know, there are only two kinds of mechanical energy that we've studied. There's gravitational potential, which we talked about yesterday, and there's kinetic, which we talked about last week. These are our two forms of mechanical energy. We're going to add a third. We're going to add elastic potential energy, but probably not today. If there's no external non-conservative forces, the total mechanical energy of a system will remain constant. I'll say that again. If there are no external non-conservative forces acting on our system, i.e., there's no friction acting on your system, then the mechanical forms of energy will remain constant. So let's talk about the roller coaster for a minute. If you've been on a Scorpion, then you know that Scorpion begins, like most standard roller coasters, with a lift hill. And that lift hill uses a chain. The chain pushes the cars up to the top of the hill, meaning an external force, the applied force from the chain, does work on the system by adding energy to the system. That's what the chain lift does. It's an external force that changes the mechanical energy of the system. It lifts the cars to the top of the first hill. Once there, the cars have gravitational potential energy. It's because they are above the reference level. Also, once there, they establish the total energy of the system. The energy that's in the cars here will be the energy in the cars everywhere. So if I know the height of the lift hill, I can probably figure out how much energy the cars have. Now, once the cars are released, they are free to go to different parts of the track. And in each part of the track, they may be exchanging the different types of energy the cars have. But the total energy will always stay the same. Again, as the cars progress through the track, they might be exchanging the different types of energy they have. But the total energy will always remain the same. For example, consider the labels I'm putting to these 4 places on the track: A, B, C, and D. At A, are we above the reference level? Yes, let's say that this is H1. If we're above the reference level, do we have gravitational potential energy? Yes, sure do. mgh1. Do we have as much gravitational potential energy as we have at the top of the lift hill? No. But the total energy has to be the same, which means whatever energy is left over, where do you think it goes? What other kind of energy do we have? Kinetic. It's the only place it can go. Which means that this amount of energy has to be equal to the energy we started with. Consider B for just a minute. Do the cars have any gravitational potential energy at B? Why? It's at the reference level. It would be mg times 0. Right? H is 0 because we're at the reference level. So where's the energy now? Do you realize now that I can just put up a picture like this and just ask you questions like, well, where is it traveling the fastest? Where is it traveling the slowest? And you should be able to reason out that the lower the cars are, the faster they're going, and the higher the cars are, the slower they're going. So here, let's do a brief amount of practice. The lift hill for the Scorpion is about 50 meters high. That's a lie. It's a number I made up to make this easy. And the radius of the loop is 10 meters. That too is a lie. I made it up to make the numbers easy. I would like you to tell me how fast the cars are going at B and at D. Let's see if you can put together what I said and use it. I'll see what you guys can do here. Let's go with like 2 minutes. Not doing what I want, but it's okay. If we're trying to solve a problem using conservation of energy, we need to have information about how much energy is at different points in the system. Now, we know here that all the energy was in the form of gravitational potential. The top of the first lift hill, the cars are barely moving, so there's no kinetic. So all the energy is in the form of gravitational potential. mgh, where h is 50 meters. So this is the energy at the top. Remember, the energy has to be the same everywhere. So I can set this equal to the energy at B. At B, there is no gravitational potential because we are at the reference level, which means all the energy has to be in the form of kinetic. Well, that's really it. We've done the heavy lifting. You should first notice that the mass cancels out. This whole term is 0. So all I'm left with is figuring out what the velocity is. About 31 meters per second. Square root of 1,000. Now, many of you are doing okay there. It was the next part you had a little trouble. But are there any questions about that? All right. Well, look, this has to be equal to the energy at D. Yes, sir?
So the velocity stays constant even at the bottom?
It's not constant. It is 31 meters per second that instant. But an instant later, it's a little bit above the background, or a little bit above the lowest level. So some of that energy has been converted back into gravitational potential. And it will start slowing down during this entire trip up to the top. Does that make sense?
Yeah.
And as we get to point D, D's going to have two forms of energy now. because we're above the reference level, there's going to be gravitational potential because we're 20 meters above the lowest point. Look, some of you got that wrong. The radius is 10, so we are a diameter above the ground. That's 20 meters. At the same time, that's not as high as the lift hill, which means the remaining energy has to now be kinetic. 1/2 mv squared. Now, all of these have to be equal. The energy at the top, the energy at B, the energy at D, they all have to be equal. So I can set any two of these to be equal to each other. I'm going to set those two equal to each other. The energy I have here and the energy I have here. I don't have to go through the middleman. The total energy should stay the same. So I'll get mg times 50 equals mg times 20 plus 1/2 mv squared. Again, I hope you notice all the m's cancel because there's one in every term. This won't always happen, but it's happening now, so I'm okay with it. So I'll have 50g equals 20g plus 1/2 v squared. So 300 equals 1/2 v squared. V equals about 24.5 meters per second. Any questions about that so far? Yes, ma'am.
Could you cancel out the G's?
No, because there's not one in every term. In order to cancel something out, you actually have to be able to factor it on both sides and then divide it away. I can't factor it on both sides. More practice is probably in order. So we're going to continue a little bit of practice, but do you now realize why no other hill on a roller coaster is ever higher than the first hill? You can't go any higher unless you add energy to the system. Now, just so you guys understand that we've been doing this all year, what we're doing right now is not new. Think of this question for a moment. You hit a baseball off your bat and pop fly. Sorry, Kyle. The catcher's going to get it. Leaves your bat at 30 meters per second. How high does it go? Look, this is a conservation of energy problem. Plain and simple. Can we all agree that the baseball is at the reference level when it leaves the bat? Is that okay with all of you? It's going to go to its highest point. At its highest point, is it moving? No kinetic energy there. One thing you could start doing is just listing out the possible forms of energy at each location. At the lowest point, is it above the reference level? If not, there's no gravitational potential energy. At the lowest point, is it moving? If it is, there's kinetic energy. At the highest point, is it above the reference level? Yes, so it's got gravitational potential. At the highest point, is it moving? No kinetic. So at the bottom, its energy is 1/2 m30 squared. At the top, its energy is mgh. How high does it go? Well, cancel the m's. 30 squared is 900, divided by 2 is 450, divided by 10 is 45. That's how high it goes. No motion equations, no seeing what 3 of the 4 motion variables I have. Energy is a clean, simple way to solve these kinds of questions. They allow us to get quick estimates. I say quick estimates because the real world does have friction and air resistance and external forces. But it'll give you an idea of what you can expect. But it'll tell you other things too, like why the lift hill of the roller coaster is higher than all the other hills. And tell you why you're going faster when you're closer to the ground. All of those things are readily evident by looking at the concept of energy. Can I keep going? Because, truth told, we do need to see some limitations. Let's go back to this question for just a minute. Just so you can start to see the difference between what you would do maybe in regular physics and honors physics versus AP1. We've already done this once. If the lift hill is 50 meters tall, and the top of the first loop is 20 meters above the ground, we expect the cars to be traveling 24 meters per second here. Right? We've already done this problem. Now look, in the real world, do you think they're really traveling that fast? No. Why? What do we have in the real world that we're leaving out here? Yes, sir. Yeah. Air resistance, friction, who knows what? It could be a bad day and there's garbage on the track too. So if you were to actually run this ride and measure the speed of the cars, you might find that they're only traveling 20 meters per second here at the top of the track. We would expect it to be 24. Maybe you measure it's only 20. Now, this is a real question. I could ask you how much work must have been done by friction. Now listen closely, folks, to what I want you to know here. We expect the energy to stay the same here and here. We expect the energy here to be equal to the energy here. If they're not, something took the energy away, or something gave the system energy. Conservation of energy tells us to expect it to be the same. But look, it should be clear that we will have less energy here than we're expecting. Where do you think that energy went? Yeah, heating up the track, heating up the air, making noise. All of these are things that take energy out of the system. If you've ridden the Scorpion, it's loud. It's not quiet. It makes a lot of noise on the track. All of that is energy that's being taken out of the system. If you can hear it, if it's getting warmer because of it, all of those things take energy out of the system. So you should expect me not to give you a problem where I say, how fast are they going at the top of the loop? You should give me you should expect a question where I tell you how fast they're going and then ask you how much energy was taken away from the system. What was the work done by friction? What was the work done by an external force? And for that, you would say, okay, I had mg times 50 here, and I don't think it's going to equal the mg times 20 plus the 1/2 mv squared. You have to understand that conservation of mechanical energy only works if they're in some kind of ideal environment. And that in the real world, we are going to have losses due to friction. And that's how we can figure out how much was taken away. We would compare the two energies that we expect to be equal and find how much is missing. Also, you guys remember those projectile problems we did for a while, right? No? Yes. I'd hate to have to offer a review. Now, you guys clearly see that you could figure out how much energy is in this system, correct? Yeah, if I told you the ball had a mass of 500 grams, You could tell me the energy in the system. What if I wanted you to tell me how high the ball went? Could you? Be careful. When the ball makes it to its maximum height, its velocity is not zero. In this instance, when the ball makes it to its maximum height, it still has its horizontal velocity. So it still has kinetic energy. You might jump to think that all the kinetic energy is potential, but it isn't. So in this case, it would have gravitational potential, plus it would have kinetic. You'd have to figure out how much of the energy is still kinetic. That's how what I'm expecting you to do will be different than what's going on in like honors and AP and regular. All right.